Good morning. This is Dr. N. Ramya, Assistant Professor from Civil Engineering Department. So here the topic is geometrical parameters of a channel, right? So in previous classes we have discussed what is open channel and what is closed conduct and what is the open channel differences between pipe flow and open channels. Like all these things we have studied, and what type of flow moving in an open channel and also closed conduct, all these things we have discussed in previous class. Now today, when you want to design a channel, right, so what are the parameters is required to design a open channel? So that's what now we are saying. Yes, today's topic is, right, the geometrical parameters of a channel, right? So it is very important to know geometrical parameters of a channel, so that it is easy to design a channel. Like, we need to know width and we need to know depth and also side slope, and what is the longitudinal parameters like length or gradient, right? All these things we should know to design a channel, right? This channel are of, again, so many types. We discuss this in next class, right? So these parameters, how we need to take a width, depth, and what is the side slope, and longitudinal parameters like length and what is the gradient, right? All these things we are going to see now, right? So yeah, and also other parameters are also there. What is that other parameters? That is area of flow. Flow means we should know what is area. Area of flow, that is nothing but your wetted area, right? What is the flow area is also called as a wetted area. And again, wetted perimeter. What is wetted perimeter, right? And what is the top width and hydraulic radius, which are used for analyzing the flow. These things, when flow is moving in an open channel, and what is the wetted area after designing when flow is moving in an open channel, what is wetted area and wet perimeter, top width of a flow, and what is the hydraulic radius, right? All these things are we should know to analyze for analyzing the flow. Right. For open channel, parameters can be defined based on the channel's cross section. Based on the channel's cross section and what is the length along the flow direction. What is the length along the flow direction. Right. For open channels, these parameters can be defined based on your cross section and its length. What is the flow moving in the direction. Right. So here, first, so in an open channel, carrying water with a free surface which is having a open channel, right? To this we are seeing a pipe, right? Pipe is nothing but your closed conduct. Pipe is nothing but your closed conduct, right? So when coming to an open channel, it is having free surface, but here it is completely closed. In this closed pipe, flow is moving, right? This is having a open structure and free to atmosphere, and it is exposed to air, right? So for this, the channel may be a natural channel, naturally formed channels, or an artificial channels. We are knowing what is open channels, right? So, and geometrical parameters determine the flow area, conveyance energy, and hydraulic efficiency, right? These things we see now, geometrical parameters, and we should know the geometrical parameters, because to design a stable and economical channel. It is very important to understanding the geometrical parameters, that is to design a stable and economical channels. So geometric influence velocity distribution, significant sediment transport and erosion behavior, right? All these things, geometrical parameters. First, velocity distribution, and what is the sedimentation transportation in an open channel, and what is the erosion. We see all these behaviors in an open channels. We should know all these things. Here, geometrical parameters of a channel. So first one is flow depth parameters. Flow depth. What is the depth of flow? So if this is your channel and I am drawing a trapezoidal channel, this is your depth of flow y. This is your depth of flow y. Vertical distance from channel bed to free surface at this section. From this is your channel bed. Let us say B. From the top width T of the flow. So the distance between a bed with the vertical distance between a bed to a free surface is nothing but your depth of flow. Depth of flow. And next, normal depth. What is a normal depth? Depth at which uniform flow occurs. This is the depth where your uniform flow occurs, and it mainly depends upon discharge, slope, shape and roughness. All these things are depends for to calculate a normal depth. Normal depth we calculate when flow is uniform. When flow is uniform flow. What is uniform flow here? Uniform flow is defined as, if you take a velocity parameter, it does not change with respect to space. Does not change with respect to space. That is equal to dou v by dou s is equal to 0. That is a constant. That is a constant. Dou v by dou s is equal to 0. That is equal to constant. Now, critical depth. What is critical depth? Critical depth, depth at which your specific energy is minimum. Specific energy is minimum. That point we call it as a critical depth. Critical depth where your specific energy E is minimum in a flow. Then that depth we call it as a critical depth. Used to classify flow as subcritical and supercritical. Flow, subcritical and supercritical. These two things are differentiated by a Froude number. Froude number. What is Froude number? Froude number is equal to your inertia force by gravitational force. Right? Gravitational. Inertia force by gravitational force. So if your Froude number is equal to 0, then we call it as a critical flow. We call it as a critical flow. If your Froude number is less than 1, then it is subcritical. Then it is subcritical flow. If your Froude number is greater than 1, then it is supercritical flow, right? So depending upon your Froude number, the flow is getting varied, right? From critical, if Froude number is equal to 1, and if your Froude number is less than 1, then the flow is your subcritical. If Froude number is greater than 1, then it is supercritical. So by using this also may vary, right? So now, sequent depth. What is sequent depth? It occurs after a hydraulic jump. After hydraulic jump. So hydraulic jump. Here after that depth we call it as a sequence depth. It also depends upon your fraud number. If this is your dam, now this is obstacle, the flow will move from subcritical to supercritical. There we see the formation of hydraulic jump. We see the formation of hydraulic jump, right? Super to subcritical flow. Then we see in hydraulic jump, change in an flow, right? Hydraulic jump. This also depends upon your initial fraud number, right? And the depth of influences velocity, energy and stability of flow. This is important to know the depth. And here main parameters. First, depth of flow. We have seen so many types of depths, right? 4 types: normal depth of flow, normal depth, critical depth and also sequent depth, right? So here the depth of flow from one bottom to your top. Bottom, the distance between your bottom width to the top width of a flow in an open channel. Then this distance is known as your depth of flow, denoted by Y. Now second one is section. Depth of flow section, right? It is a depth of flow normal to the bed of the channel. Normal to your bed of the channel, right? That is denoted by D, and D, the equation is Y cos theta. Y cos theta. To know the depth, what is the equation? D is equal to Y cos theta. I'll explain you next images there, right? And theta, what is theta? Theta is the angle which making the channel bed to the horizontal. The channel bed makes with the horizontal. That is your theta. It is an angle. So here, if you see here, this is your depth, which is normal, right? What is this? This is the depth of flow in vertical direction, right? This is vertical direction Y, and this is your normal to your bed channel D, right? So the angle between D to Y is nothing but your theta. D to Y is nothing but your theta. So I want D. So what I will do? D is equal to Y cos theta. Right? So if the slope of channel are very small, if this is your formula. If your channel slope is very small, then what happens to your cos theta? That is equal to 1. That is equal to 1. Then what happens to your D? Y cos theta in place of cos theta, you put 1. So that your D is becoming a Y. When the depth of flow at section and the depth of flow both are becoming equal, right? The depth of flow and depth of assumed equal unless mentioned otherwise. Right? So why? This is what your open channel section is. Now top width T. This is your channel, this is your top width T, bottom width, angle, right? dy. These things are very important to know, right? Top width. So it is the width of the channel at the free surface, the width of the liquid surface exposed to an atmosphere. The free surface which is getting exposed to atmosphere, it is known as a top width in an open channel. Now wetted area. So what is the area wetted in the open channel? So area which is got wet with the flow, that is your, this portion is your wetted area, right? We say the formula now. here wetted perimeter, right? Wetted perimeter. So area depends upon your perimeter, and area, all these things depend upon your geometry. If your geometry is square channel, if your if your geometry is your square, then the wetted area. If your geometry is the triangle one, calculate the wetted area of the triangle. If your geometry is rectangle, if your geometry is rectangle, this is your wetted area. So calculate your area of the rectangle, right? Depends upon your geometry. Mainly wetted area and wetted perimeter, right? If your is square, the wetted area is side into side, right? So like that, depends upon your geometry to calculate velocity, to calculate area and perimeter both. It is the length of the channel boundary in contact with the flowing water at any section. So wetted area, this is your wetted area and wetted perimeter, right? So what is the wetted perimeter? So depending upon your geometry. Now hydraulic radius. Hydraulic radius is a very important one. It is a ratio of cross-sectional area to the perimeter to cross. It is a ratio of your cross-sectional area, that is wetted area, to wetted perimeter. To wetted perimeter is called as hydraulic radius, are also called as hydraulic mean depth, are also called as hydraulic mean depth. So R is denoted by wetted area by wetted perimeter. R is equal to A by P, right? So here is the geometry. This is a rectangular channel and here is the circular pipe running full, and this is what a pipe not running full. So three conditions are there. So what is the hydraulic radius for the rectangle open channel? Is R is equal to A by P, and area is equal to, what is area? This is B into depth of flow, Y. B into Y. And what is the perimeter? B1, Y1, 2, 1, Y. So these two. So B plus 2 times of Y. Wetted perimeter. This. Only we got wetted. This is what your wetted perimeter. So formula is By by B plus 2Y. 2 times Y plus Y. So 2Y. Is it clear? This is what your Reynolds hydraulic radius or hydraulic mean depth for a rectangular channel. This is for rectangular channel. Right? Now, pipe running full. Pipe running full. So, area of your pipe and perimeter of your pipe. What is an area of a pipe? Wetted area means completely is running full. So, complete the circle is getting wet. So, area of a circle is pi by 4 d square. Pi by 4 d square. And what is perimeter? It is 2 pi r. 2 pi r in terms, we can write d also. Right? D. I am writing here pi d. So dd gets cancelled, pi. So what is the formula we are getting? D by 4. The hydraulic radius of a circular channel is A by P. Wetted area by wetted perimeter. Right? So now pipe not running full. If pipe is running full, it is easy to calculate area of circle and perimeter of the circle. So what we are getting hydraulic radius as D by 4. When coming to your pipe which is not running full, here is the problem, and here is the formula is somewhat difficult when comparing with all others. Right? So here, what is the area of a pipe not running full. So this is what, yeah, wetted area and wetted perimeter. You have to calculate for this. This one is open. This one is no flow here, right? So A by P. A, what is area for this? It is R square by 2 into 2 theta minus sine 2 theta by 2 R theta. R square by 2 into 2 theta minus sine 2 theta by 2 R theta. Right? This is what equation of hydraulic radius which is not running full. Now, next hydraulic parameter is hydraulic depth. So, here hydraulic depth is the ratio of area to the top width. Hydraulic depth, capital D, is denoted by your area by your top width, T. Top width, if this is rectangular channel, this thing completely is your T, top width, right? So, wetted area by T is your capital D. That is hydraulic depth. And what is Manning's roughness coefficient? Roughness coefficient is a channel roughness, a measure of channel resistance to flow used in calculating the flow velocity. When you to calculate the flow velocity, we use a Manning's equation. What is that Manning equation? V is equal to 1 by n, r to the power of 2 by 3, s to the power of 1 by 2. 1 by 2, r to the power of 2 by 3, s to the power of 1 by 2. A root is. This is what your velocity by using a Manning's equation. Right? Now, geometrical parameters means mainly depending upon your cross section, your channel, wetted area, wetted perimeter will change. That also hydraulic mean depth is also changing, right? So if how the cross sectional shape is and which one is easy to calculate all the top width and all the parameters of the channel to design, right? So here rectangular section, if the channel is rectangular, it is very easy because whatever the bottom width B is there, that is your top width T. Bottom width and top width both are same, and it is easy to construct and analyze the flow, right? And the depth and width are easily measurable. This rectangular depth we can easily measure what is B and what is D. If we know B, that is your D depth. The Y may change, the depth of flow may change depending upon your flow rate, but it is B and T does not change because it is a rectangular channel. It is a rectangular channel used in this rectangular channel is used in flumes and channels. Used in flumes and channel with lining. Yes, lining word. Lining. What is lining? In previous also I think we have discussed. Lining means that we use here materials like we make this smooth by using some cement or by using concrete and by using soil, clay soil. We make it as a completely prismatic, which is having a definite shape and size. So by using these materials, we make this a lined. So the resistance get reduced, roughness also reduced, right? It is used in a laboratory flumes, this rectangular channel section. Now, trapezoidal channel section. So trapezoidal channel, it is most commonly used in irrigation channels, and this is trapezoidal section. Channels are mainly used in many irrigation engineers. Right now, side slope makes structure stable and reduce erosion. Here, in rectangular channel, the best channel section we call here as a trapezoidal channel. Best channel section we call here as a main the trapezoidal channel, right? So here, if this is your trapezoidal channel, it is having a slope here. So by this slope, the structure, the flow is easy, and the eddies formation at this angle is less, right? Let us take 120 degrees. When you use this as 120 degrees angle trapezoidal channel, then the erosion and the eddies formation at this corner we see less. So the whatever the flow is, that flow we see at other end. The energy loss is also, the head loss is also very less when comparing with the other channels, and also it reduces the erosion, and it provides economical flow with minimum perimeter for given area. It is minimum perimeter with given area. It is very economical when comparing with the other rectangular sections. When if you see, this is your rectangle, and here due to the eddies formation at this corner is more. It is completely at 90 degrees. Right now, for this it is easy at 120 degrees trapezoidal channel. Circular section and parabolic natural section. These are another type. The third type it is here the circular section used in sewers and drainage systems. The circular pipes we use. If the pipe is full, it is pipe flow. If pipe is running off, then it also called as an open channel. Open channel. Right? So this efficient under full and partially full condition. Full condition and partially condition also we have calculated hydraulic radius, hydraulic mean depth, right? So providing self-cleaning velocity with minimum head loss. For this we are providing a self-cleaning velocity flow with minimum head loss. The minimum head loss is very less when comparing with the other channels. Now parabolic and natural section. So here found natural streams, shape governed by sediment load and boundary conditions, and it is very complex geometry but hydraulically efficient. Irregular naturally formed channels, right? Natural streams, and it is governed by your sediment loads and boundary conditions, and it is very tough to complex for geometry, but it is hydraulically efficient. The natural section is. Now side slope and bed slope, right? Side slope. Side slope is the ratio of your horizontal and vertical dimension of a channel sides. If this is your trapezoidal channel, this side slope. This is your side slope. If one vertical and one horizontal, then the angle between this is 45 degrees. So this is what the horizontal and vertical dimensions of a channel is. That is your side slope. Now steeper slopes may cause failure or sliding. Steeper slopes may cause failure or sliding, and gentle slopes ensure structural stability and reduce erosion. So depending upon these slopes also, the flow may varies, right? Now bed slope means we know that whatever the flow in an open channel, that is because of your gravitational flow. Gravitational flow, right? If the channel is having slope, then if channel is having a slope, this is what your bed slope is, right? Side channel slope is this one, Side slope is this one. How much shifted to vertical or one horizontal depending upon your slope. This is your side slope. And here is your bed slope, slope of your channel. So it determined by the gravitational force available to flow easily in an open channel. And higher slope, higher velocity, risk of scoring. If slope is higher, if the slope is like this, the flow moving with the velocity is also high. The risk of the erosion is also high. Scoring formation is also high. If the slope is less, like this, if the slope is like this, then the sediment deposition and reduced capacity. So proper selection is very important for stable and self-cleaning channels. It is very important to know the slopes. Side slope also is also an important one, and also bed slope. What type and what slope we have to design a channel section for economically. Now velocity distribution is also important parameters, is a very important parameter, right? Maximum velocity found slightly below the free surface due to reduced friction. The velocity, if the depending upon your channel sections also, the velocity distribution may vary. If your channel is the rectangle type, and here we see one type of velocity distribution. This is what your velocity distribution profile of a channel, right? Of a channel. If for a pipe it is parabola, but for rectangular channel, this is what your profile is. So depending upon your channel, we see different types of profile. Near channel beds and walls, velocity is very low. At the boundaries, obviously the velocity is less because of the boundary layer, because of the boundary shear, because of the frictional resistance. We see very less velocity at the boundaries. Distribution depends on roughness, channel geometry, and turbulence. This distribution also depends upon your roughness of the channel, roughness of the channel, and channel geometry, and also turbulence. Important for sediment movement and erosion prediction. It is important. And non-uniform velocity affects energy loss and also flow stability. Hydraulic jump geometry. So hydraulic jump, when you change a flow from supercritical to subcritical, we see the formation of hydraulic jump. That is what, if fraud number is greater than 1 and fraud number is less than 1, when the flow change rapidly, sudden variation we see in hydraulic jump, right? And next, hydraulic jump, difference between the sequent depth we see, and associated with the higher energy dissipation, very high energy dissipation we see when hydraulic jump occurs, and used in spillways, drilling basins for energy control. This we see drilling basins and for energy control. The geometry depends on your initial depth, velocity, and fraud number. This hydraulic jump height. Hydraulic jump height depends upon your fraud number and the spillway type, and what is the initial depth, and what is the velocity of the flow, and also fraud number. And which one is the economical channels among all these things? The maximum discharge for minimum construction cost. That the main goal of the channels is what? That you should carry maximum discharges with minimum cost. That should be economical, right? And achieved by minimizing wetted perimeter for a given area. achieved. This goal will achieved when your wetted perimeter for a given area is minimum, right? For rectangular channel, best to when width is equal to 2 into y. So this is what your channel is. This width for rectangular channel, this b should be of your 2 times of your depth of flow. Then your rectangular channel section is economical. When the width is your 2 times of your depth of flow, then the rectangular will become economical channel section. Now, when trapezoidal will become economical? When your half top width. That is, if this is your channel and here this is what your T is. So, when your half T, that is T by 2 is equal to side slope S naught into depth y. Then your trapezoidal channel will become economical, ensures high efficiency with minimal material usage. And these are the applications. Example: irrigation channels, controlled geometry, improved distribution, and urban drainages prevents flooding using optimized channel section, and stormwater drains handles large peak flows effectively. Rivers and natural streams. Understanding geometry helps predict flood behavior, and flood control structure like hydraulic jams and energy dissipators designed using the depth and slope geometry. This is the applications of your geometrical parameter. Here are the references. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.